It's all better now. Yep, and I have a whole bunch of stuff I posted on YouTube that is illegal because it has student faces on it, so I have to go back through and take it all down because I forgot to pin the video. All right, work and energy. Now, on Tuesday, I probably did this in class. I unfortunately, probably freaked a few people out with the idea that when we calculate work, we are going to have to be doing this integral, and that work is going to be a mathematical nightmare for some of you because you haven't gotten integrals yet, and you're afraid Mr. Shelton's going to expect a lot of calculus out of you. Nothing can be further from the truth. You are very seldom ever going to have to use this. Although it is true that work by definition requires the integral. It requires a sum. And I need you to understand why this is true. And this is not for the folks who who've never had physics. This is for everybody. You have to kind of get this idea that work is an incremental process. If I apply a force to this box in this direction to move the box a small distance, that's what dx means, a little tiny distance. And then the box moves that distance. Unless I apply the exact same force the next time, I could use, say, this force now to move the box a little tiny distance. The amount of work I would do here might be different than the amount of work I did the last little tiny distance because I've changed the size of that force and I've changed the angle. So although the box moves my little tiny distance now, this amount of work might be different than the last little bit of work. The idea of the integral is that it takes into account little changes in force that might occur as you're moving the box from here to here and adds up all of those little bits of work that are done. That's what the integral means. In practice, and this is what you're learning in calculus, that there is a procedure that you can do whenever you have an integral that will produce an answer based on those changes in the force over the course of the displacement. That's what the calculus is. It's a function. It's a procedure. And you'll learn that in calculus. But I need you to recognize that we only have to use this if the force is not a constant. If the force applied to the object is a constant, then we always downshift into the algebra version of this. And this is what's taught in Honors and AP Physics 1, the algebra version. But it fits most 90% of all roles. It's really what you want to recognize as the way to do things. Now, there's a couple pieces here, and each one of them is important. So let's back that box up. First, there is the displacement. Please recognize that when we talk about the displacement, we are specifically talking about a change in position of an object. If an object's position doesn't change, no work was done. So when we talk about work, we are specifically talking about something that will occur to change the object's position. Now, in the course of doing work, we have to apply a force. We talked about that as well, which means that there needs to be a component of the force in the direction that moved the object. Meaning the force has to be in some way responsible for the motion of the object, or else it's not doing work. Now, that's what that angle's about. Verifying how much of that force is actually doing the work on the object. So when we talk about the force here, we're talking about the force directed in the direction of the displacement. That's the part of the force that's doing work, and that's why it's a cosine. So in my diagram, it'd be the force that's this way. Sometimes it's called the force parallel to the direction of motion. In fact, in some textbooks, they will write this as F with little parallel lines next to it times delta X to drive home the fact that we're only talking about the part of the force that's in the direction of motion. Now, here's the big thing, and the part that I really want you to hammer down on your work there, because this is where we start to get into the tricky part of this. more than one force can do work at the same time. If there's more than one force acting on the object, then maybe multiple forces are doing work on an object at the same time. For example, this force that I've applied here, I think you can imagine a person applying a force to an object and that object sliding across the floor. So that object might move from here to here across the floor. And it might happen because this force is acting on it. Now, if I tell you that the ground is frictionless, then you could probably imagine that by the time the box makes it to here, this was an unbalanced force acting on the box. And therefore, the box is likely to have some velocity when it gets here. So the work not only changed the position of the object, but the work very likely changed the velocity of the object. And this isn't an accident. We know all about this. And I hope that I talked about this on Tuesday, but if not, net force equals MA. So if my work is equal to net force, an unbalanced force, times delta X, then my work is equal to MA times delta X. And I want to remind you, 2A delta X equals V squared minus V naught squared. Motion equation. If we're dealing with a constant force, we're dealing with a constant acceleration. I can use a motion equation as substitution here, which means I can substitute in m times 1/2 V squared minus 1/2 V naught squared. I'm still talking about doing work, but now I have an expression for work that's based on a change in velocity. Look, it should be really clear that it's been much easier for us to measure velocity this year than acceleration, much easier to measure velocity than measure force. So we can express how an object's energy changed by looking at its change in velocity. And that's what this is about. Now, it should also be, pretty apparent that we have a name for this expression, that this is kinetic energy. And what we're saying here is that if work is being done by an unbalanced force, then you can measure that work by looking at the change in kinetic energy. Now, that's where I would have left you on Tuesday if things had gone well. Here's where we have to kind of dive into the details here. There's seldom just one force acting on an object. Most of the time, there's multiple forces acting on an object at the same time. And one notable thing would be if you're pulling something across the ground, there's likely going to be friction acting at the same time. Now, friction does work. It's a force that acts on the object as it moves. The thing about friction, though, is that friction almost always, in fact, I think it's going to be, for the time being, it's going to be every single case until we start dealing with things that roll. Friction is going to do negative work. And I want you to see why. It should be obvious, but it might not be obvious for everybody. If the object's going to travel this way, when we look at the work being done by friction, technical definition of work is going to be the size of the force times the cosine of the angle times delta X. But friction always opposes motion. So we know that in this circumstance, the friction is going to be in the opposite direction of the displacement. In this circumstance, that has to be true. So if I was looking at this one where the box is sliding to the right and friction is acting to the left, I would have to put 180 degrees in here for that cosine. Because I have the displacement this way. Hi, Mom. It's nice to see you, Mom. Now, I think you all know that a cosine of 180 degrees is going to be negative, which explicitly indicates that this will have a negative amount of work. Now, I'm going deliberately slow, mostly because I want to make sure that these little details aren't lost. I pull on a box. I give the box energy to move it across the room. If there is no friction, when I let go of the box retains that energy because it has now kinetic energy. Its velocity changed. But that doesn't mean that that's what really happens in the world. It could be just as straightforward that I gave the box energy, moving the box across the room, and at the same time, friction was taking that energy away. I could do 200 joules of work on the box, and at the same time, friction could do negative 200 of joules of work on the box, which means at the end, the box has no more energy than it had before. It's in a new place, but it doesn't have any more energy. The 200 joules I gave to the box got left as heat on the floor as the box slid across the floor. Because for every joule of energy I gave the box, friction took that work and did negative work on the box at the same time. So this whole idea that work is equal to the change in kinetic energy, that's only true when work is being done by an unbalanced force. So in your notes, be careful here. There has to be a net force, something unbalanced, in order for that to be true. That does not tell you the work done by an individual force. So what if the frictional force that was here wasn't a large frictional force, but was relatively small, like just a little bitty frictional force? There's probably an unbalanced force here. The box probably has velocity when I'm done and has moved. I could figure out the net change in energy by looking at the change in kinetic energy. But that's probably not how much work I did on the box. I probably did more work than that. But friction took some of it away, just not all of it. So when you're trying to keep notes here about what I think is important, is that there's a difference between finding the net work being done on a system and finding the work done by an individual force. So what I'd like to do is an example that illustrates this. So here's an example that will illustrate this point. And what I'm going to do is, I think you have all the tools for you to do this on your own. And I'm going to make this a kind of a problem where you guys work it, and then we'll come together and I'll hit on some different folks to kind of tell me about what they did. But let's consider this. There's a 5 kilogram box. I'm going to pull on it with a 25 Newton force at an angle of 30 degrees. Okay. There's a coefficient of friction of 0.2. Now, let's say we drag the box 10 meters across the floor. I want you to find the net work. I want you to find the work done by friction. and a work done by FA. Okay, let's practice. So see if you can work that out. It's not terribly hard, but this is for all the folks really who haven't done this in a long time, to give them a little bit of, or I've never done this before, to give them familiar with how this works. So I'm gonna do something I'm not very good at. I'm gonna shut up and give you guys a chance to try this out. Okay? I'm just gonna suck coffee. Hello, somebody has their mic on and we can actually hear them writing. That brings me happiness. It's commitment. That's a really loud pencil though. Oh yeah, I said I'd be quiet. Man, bad at my job. Now, if you want to check your work, think you can. When you guys are ready to talk about it, give me a yes in the participant window, please. And then I'll know. All right, so that's a lot of you, 14 out of 22. Hope you got some of these answers, but the first one to do is this one. This one's the easiest one to do. It's just straight application of our formula. It's 25 newtons, that's the applied force, times the cosine of 30 degrees, that's the angle between the force and the displacement, times 10. So that one should have been straightforward. The work done by friction is a little bit harder because there's no way around it. You've got to figure out the size of the frictional force. And that's what makes it tough. So the frictional force is equal to mu times the normal force. When I look at the forces, and yes, you have to do the whole thing. You've got to do normal, you've got to do weight, and you got to do the fact that there's this F sine 30 degrees here. That's reducing the size of the normal force. So when I found my answer, I had to do, the normal force was 50 minus 12.5. And so it was 0.2 times 50 minus 12.5 for the frictional force. It is possible, though, I think I just did 12 because I was in a hurry. So 50, enter 12.5 minus times. So I got a frictional force of 7.5 newtons. So this should have been 75 joules. Now, you can just add the two things together to get this. But I want to point out that you could do net force in the x direction, which would have been F cosine 30 minus friction. You could do net force in the x direction. Add those together, and then take that and multiply by delta x. Give you the same thing. But when you can just add them together and get this answer, that's probably the way to go. Now, I don't know whether you find this to be challenging or not. I do want to point out that there's nothing wrong now with saying, how fast is it going when it gets here? This is the change in the energy of the system, which means when it gets there, it has kinetic energy equal to 1/2 mv squared. If I want to know how fast it's going, I just set the net work equal to 1/2 mv squared, and that tells me how fast it's going. Skylar? Oh, I thought you put your hand up. Okay. So as a straightforward example goes, how do you guys feel about this? Is this easy, hard? This is not the level of the AP exam, but it's not far away from it. So I want to be really clear. They're going to ask different questions than this, but I'm hoping that this wasn't too terrible. All right. Let's talk about a few other little things then. That is the extent of what I think you guys will need to be able to do when it comes to work, but there's a lot of different arrangements of what you're probably going to expect to see. So every single force problem that we've had this year can be turned into a work problem by looking at the results of that force acting on the object, which means every time there's been more than one force acting on an object, we could evaluate how much work was done for the object making that particular travel. So consider, all of these, inclined plane problems now. Every one of them now is a discussion about how much work was done by this force. Now, this problem is not as easy as it seems right off the top. I want you to consider this. Let's consider a ramp question where the ramp is 10 meters long. I don't know why I drew that there. 10 meters long. Let's say it's that same 5 kilogram box. Let's say I'm applying a 25 Newton force, and I'm applying it horizontally and it's a 30-degree ramp. Now, asking how much work is done on the box, even if I say that this is frictionless, the amount of work done on the box is deceptive here. It's not enough to say the work was 250 newtons. That makes sense. That's how much work this force did on the box. But do you realize that another force was doing work on the box? And this is where we have to be really paying attention. The box has weight, which means that there is a portion of the force in this direction. That force is also doing work on the box. It's doing negative work on the box. So although I did 250 newtons of force of work with, I'm sorry, I put newtons. What the hell am I thinking? I did 250 joules of work on the box, pulling it up the ramp with my applied force. There is work done by gravity. And that's going to be mg sine theta times the cosine of 180 degrees. Be careful here. We're talking about two different angles now. This is the part of the force down the ramp. It acts in the opposite direction of motion. So this is the angle of the ramp. This is telling me how much force was down the ramp. But the box moved in this direction. So this angle is the relationship between going up the ramp versus the force down the ramp. Times 10. It's not very much, but it makes a difference here. So I believe that's going to be that can't be too, I can't do the math in my head. Sine of 30 degrees is a half, right? So 50 times 0.5 times -1 times 10. So negative 250 joules. So what does that tell you? When I get up to the top of the ramp, the box has no velocity. Net work done on the box is 0. It's true. I pulled with a force that was equal to the force down the ramp. So the box moved up the ramp at a constant velocity. I never changed its kinetic energy. I merely moved it from the bottom of the ramp to the top of the ramp. I did 250 joules of work. Gravity did 250 joules of work. Does that make sense, guys? So when we're calculating work, you just need to be aware. Now, I do want to show you one final thing. And when is the bell ring? I never remember. There's no bells, I know, but I'll make a bell noise. Okay, so I have 8 minutes. This is not what I would have done last year. So all of you who were in my class last year, we didn't do work problems like this. They were pretty light. I want you to think for just a minute about framing this problem a little different than what we just did. And I really just want to focus on the work done by gravity. So I'm going to focus on just this force. And again, we're going to say that the box went up the ramp all the way to the top, a distance 10 meters from the ground. The displacement of the box was in this direction. That's the displacement of the box. Weight acted straight down. So what is this angle? Can you mathematically work that out? I mean, I can. I want you to. It's 120 degrees. If you don't know where I came up with that, I mean, I just came up with looking at, this angle has to be 60 degrees because this angle is 30 degrees. Is that okay? So this one here has to be 120 degrees. Am I okay with that geometry? I need you to have this geometry skill. I can show you this another way if you need it, but please tell me we're okay with this. Riley, you okay with that? I'm just looking at faces trying to see if everybody's okay with that. All right. If you walk with me on this one, the work done is, remember, F cos theta times delta x, where this is the angle between your displacement and your force, which means I could have written this as mg cosine 120 degrees times delta x, because that's the angle between my displacement and the applied force, which would have been 50 cosine 120 degrees times 10. You type that into your calculator is going to give you a negative answer, because the cosine of 120 degrees is negative 0.5. Right? It's a second quadrant cosine, so it has to be negative. So this, by definition, will give you the negative 250 joules, because it has to work this way. So when we calculate work, when you're looking at problems, you really only need this. You don't always have to downshift into figuring out forces and finding components and stuff like that. It's all built in here. It's already taken that into account. Now, finding friction, you're going to have no choice. Finding friction is going to mean getting the normal force. And the only way to get the normal force is by resolving forces. There's just nothing else you can do there. But a lot of these other ones, look at the angle between the force and the displacement. All right, that's it for today. I'm going to finish a few minutes early. That's probably not going to be a problem for anybody. But basically, you guys get to finish early because of my bladder. Sorry, I know. But I'm so excited that I don't feel like I have to sterilize myself after I come back into the room and touch things. It's kind of nice. It makes for a weird day. And for some of you, this is what my face looks like. Yep. Never seen me without a mask. This is it. I mean, a lot of you have, but some of you haven't. This is it. This is the real thing. It's not better. I know. You probably wish I had my mask on. And I can empathize with that. I really can. So, well, guys, this has been fun. I'm going to let you all go. I look forward to seeing you all tomorrow. And don't forget, I will keep my promise. You'll see a grade put in today. You don't have to do anything about it. It's going to say due today. But if you were here today, you're going to get a little bit of extra credit. It's going to say it's going to be out of 0 points, but there'll be some points in there. All right? All right, guys, have a good day. I'll see you all tomorrow about this time in these little boxes. So, bye-bye, folks. Have a good day.
See you, Mr. Shelton. Have a good day.
Thank you. You too.
Mr. Shelton,
Yes.
do you have a class next period I can sit in for? Because I may not be here 6th. Or do you have research?
My next one is my research class.
Okay.
Yeah.
I'll probably just watch the video then.
Okay. I'm sorry. Yeah. You have
That's
something
fine.
going on?
Yeah. I got to pick up. There's debris everywhere. My mom lives really close to the water. So it came up and I had to go shovel. All right.
Sorry, man.
That's
Good luck.
fine. Yeah. Thank you. All right. Have a nice day.
Talk to you too. Bye.